Welcome. My name is Brett Bott, and presented here is my undergraduate research in synthetic organic chemistry. My project title is Two-Step Synthesis of Novel Boronates, Structural Building Blocks of Therapeutically Relevant Compounds. The purpose of this project has been to synthesize a library of novel boronates, which can be seen here in Figure 3, through a simple two-step synthetic process. These compounds are classified as boronates due to the presence of a boron atom within the compound. Compound libraries such as this one provide a sort of cookbook for chemists to easily synthesize these smaller structures for the use in the construction of larger therapeutically relevant compounds. The two-step synthetic pathway is outlined here in Scheme 1. The first synthetic step is called a homologation reaction and results in the strategic placement of a chlorine-containing carbon atom adjacent to the boron atom. The second and final synthetic step is a bimolecular nucleophilic substitution of the chlorine atom with an R group. The term R group is a placeholder and represents a diverse group of possible substituting compounds. Looking at the boronate structures in Figure 3 should give you a good sense of what an R group can look like. At this time, 15 of the proposed structures have successfully been synthesized, and each synthesized product characterized through proton NMR and GC mass spec. Our 15 synthesized products are denoted by red boxes around their compound number. The majority of the boronates have proved to be stable in silica gel, which allows them to be purified without expensive equipment. Through the creation of this library, we've also investigated physical and chemical limitations of our synthetic pathway. Unsurprisingly, the size of the substituting R group has been the largest factor affecting our product yield. Our goal here has been to generate a library of boronates that will be relevant for drug development. To increase the viability of these compounds as potential precursors, a chiral directing group can be utilized to obtain enantiomerically pure compounds. The term enantiomer refers to the orientation of specific bonds within the compound, and it is crucial for drug development that the correct orientation is produced every time. Scheme 2 shows how a chiral directing group is attached prior to the homologation step. So why do we care about boron, and why do we care about its use in drug compounds? Well, boron is a unique atom and it has characteristics of both metals and nonmetals. And because of these unique properties, some boron-containing compounds have the potential to be very powerful drugs. Just over the last 6 years, the FDA has approved 3 boron-containing drugs, which demonstrates a growing role for boron as an active component in medicinal compounds. Thank you so much for your time. I would like to thank my research advisor, Dr. Fabry, instrument technician, Cindy White, chemistry safety officer, Ian Seiler, the Office of Undergraduate Research for partial funding, and the College of the Sciences for partial funding through the SURE grant.